Hello students, welcome you all again in this part of my lecture on fluid power control. Here the list of the chapters we have already completed. There is hydraulic cylinders, hydraulic actuators, but obviously on motors and rotary actuators not yet completed. In the control components, pressure control valve and directional control valve is already done. Today I'll start discussion on flow control valve, FCV. So flow control valves, as the name suggests, it controls, rather they control the rate of flow of fluid through a hydraulic circuit, and FCVs accurately limit the fluid volume rate from a fixed displacement pump to a branch of circuit. Okay, so what have I said is it controls the volume rate, okay, of the fluid. So we can say its function to provide velocity control of the linear actuators, as well as it can control the speed of rotary actuators, as it is being shown here. And typically these kind of valves are used in regulating cutting tool speeds. See, in manufacturing process there is a huge application of fluid power control to regulate the cutting tool speed, right? Definitely not always it will be using the same speed, okay, but we have same pump, right, fixed displacement type. So how can it control the speed? Using FCV. It can control the spindle speed, okay, speed of surface grinder as it is mentioned here, and most important one, it can control the travel rate of vertically supported loads, right? So our load is supported vertically and it is moving upward, downward by forklifts or dump lifts, right? What is the speed, travel rate? Okay, that can be controlled by this FCVs. Fine. So here if you summarize the functions of flow control valves, we can have our first point as it can regulate the speed of linear and rotary actuators. I have mentioned earlier, but here is how we know speed of actuation is Q by A, right? Linear speed, if the question of linear speed comes, Q by A, okay, yes, Q by AP. So definitely AP is constant, so if we can control Q, the speed can be easily controlled. Okay, then it can regulate the power available to the sub-circuits by controlling flow to them. Okay, that means there may be various branches of one circuit known as sub-circuits, and the power available to that sub-circuits can be controlled by FCVs, because all the branches are connected to a same pump, okay, constant delivery time. But we may need, as we needed controlled pressure in some branches of circuit, and that was done by pressure reducing valve. Likewise, we may need controlled speed in some part of the circuit, right, and that will be done by FCVs. So whatever may be the flow rate delivered by the pump, constant displacement type pump, FCV, if fitted in any branch of circuit, it can control flow downstream to it, and thus the requirement of sub-circuits can be maintained. So power required in that sub-circuit, that is, power is Q by P. So if pressure is predetermined one, Q is controlled by FCVs, then power required by the sub-circuit can be easily controlled. The last point is it can proportionally divide or regulate pump flow in various branches of the circuit. Right. See everybody, as I said, flow control valves allows one fixed displacement pump to supply two or more branches of the circuit, right, at different flow rates, obviously on priority basis. Which part of the circuit requires what amount, okay, they can control, right, and it should be controlled, because if those branches are left unrestricted, then definitely branch circuits may receive an oversupply of the fluid, right, and which in turn can operate them with greater speed than the specified one, than the required one, and definitely it can increase the chance of damage to work, to hydraulic system, and definitely to the worker. So that is the function of FCVs. And here is the working principle. FCV is nothing but an orifice, okay, definitely not, usually not the fixed area type, okay? And the working of orifice, we have gone through it in our fluid mechanics class, okay. What happens as flow is flowing through orifice? Definitely there will be a drop of pressure, and because of drop of that pressure, flow will be controlled. I mean, orifice is nothing but a resistance to the path of the fluid flow, okay. So definitely a partially closed, okay, orifice or flow control valves in a fluid pressure line, hydraulic pressure line, causes resistance to the pump flow, and this resistance definitely alters the flow rate, right. So flow control valve, nothing but some orifice. And you can recall usually pressure measuring devices are fitted upstream and downstream of the orifice, where we can find the difference in pressure by using a differential manometer. We can find out that, right. So if we can measure the pressure difference across the orifice, we can find out the flow rate through it by using this equation. That equation we are not going to obviously derive. I hope you can recall from your fluid mechanics class. Flow rate of flow through orifice is this. CD is coefficient of discharge, AO is area of the orifice. Right at that moment, P1 minus P2 is the drop of pressure across it. P1 is upstream pressure, P2 is downstream pressure. Rho is density of the fluid. So that is Q, flow rate through orifice. We want to control that Q, right? Okay. Usually it is done by controlling AO, I mean area of the orifice. And this area can be controlled by various kinds of construction. Here is one of them, butterfly type. So definitely, as you can see here, if we control this butterfly valve here, this one, so definitely flow can be controlled through it, okay. As it is being shown here, it is fully closed, right, and here it is fully opened, right. So definitely as we revolve it, so it can finally reach to this completely closed condition, and in some intermediate condition it will give us partially open type, and definitely the flow through it can be controlled thus. Now I'll just describe here the operation principle with the help of this circuit. So here is, in this circuit, there is one piston cylinder arrangement, there is one load. Here is the piston cylinder, here is the load, here is a direction control valve, and what are there? There is obviously the pump set. Here is one PRV, and there is the FCV. It is marked by this circle, shaded circle. That is the FCV. Okay, I have not formally disclosed the graphical symbol, but you can come to know here how it's going to be. And as I said, it is nothing but an orifice with changeable areas, and pressure gauges are fitted across it, as it is being shown here, P upstream. So this is the upstream one, pressure gauge fitted at the upstream, and here is pressure gauge fitted in the downstream. Okay, and what we are expecting: flow from pump through FCV, through this DCV, reaching the blanket side. Okay, and it will be pushing this piston towards left. Okay, fine. Now assume it is a pump is supplying 10 liters per minute. Okay, constant displacement type pump, constant discharge type pump, 10 liters per minute always. Okay, irrespective of the situation in the circuit, 10 liters per minute. And initially assume FCV is completely opened, right? I mean, putting no restrictions in the path to the DCV to the actuator finally. So definitely there won't be any pressure drop across the orifice, across the FCV, and pressure gauge upstream, pressure gauge downstream showing the same pressure. Now say we have changed the area. Okay, we have changed the area by some means. How can we change that area? That will be discussed later when we will consider the working principle. And the moment we change it, that means we are putting some restrictions. Definitely flow through it will reduce, right? And say now flow through the orifice becomes 4 liters per minute. Just assume. But pump is supplying 10 liters per minute. So this excess 6 liters per minute, where will it be going? Because pump will be continuously supplying. But in FCV restrictions is such that it can allow 4 liters per minute here. Right? So definitely there is another bypass line here, and that is nothing but this branch, means PRV, right? So definitely, since here 6 liters per minute may get accumulated, okay, and definitely we won't allow any accumulation, otherwise it can burst. So definitely this PRV will get activated, and these 6 liters will flow through this to the tank per minute, right? That means the moment we put some restriction, we control the area of orifice, at that very moment PRV will get activated. Then can I ask you, what is going to be the flow rate through FCV? That is 6 liters per minute, as I have already said. Okay, but my question was, what is going to be the pressure here? Yes, definitely this pressure, okay, will be the PRV setting, okay, because it is connected, the upstream side that means PIV side, okay, of the FCV. So this pressure gauge means this pressure gauge will be showing the PIV setting always, the moment we control area in FCV. Okay, right. So one important thing you have come to know, that the moment FCV gets activated, okay, area of the orifice of FCV is controlled, pressure upstream to it always the PIV setting. Okay, and from here, from using this expression, we can find the flow rate through it. CD manufacturer will supply. A is the area of the orifice. P1 minus P2 the pressure drop. We can find it from the pressure gauges, and we can find. So for your reference, I have written some important things related to FCV. That is, the resistance offered by the orifice raises the pressure upstream to the orifice to the level of relief valve setting, and any excess pump flow passes via relief valve to the tank. I will explain. Here it is written for your reference. Now the classification of FCVs, they can be classified in two heads, broadly under two heads: non-pressure compensated type and pressure compensated type. What do they mean? I'll explain. But here is the non-pressure compensated noodle valves, or the FCVs. The schematic diagram of non-pressure compensated type flow control valve are shown here. This one, that's the schematic. Sometimes these are called needle valves because the shape of the adjustment knob or the valve stem, okay, it is needle shaped. If we adjust the knob from outside, then definitely the area through which flow is taking place can be adjusted. Okay, that is the simplest type of flow control valve. It consists of a screw or a needle inside a tube-like structure. So here is the tube-like structure, right? And here is the little adjustment knob. At the end of adjustment knob, it's a needle. Okay, right. And this adjustable orifice can be used to reduce or to increase the flow through the circuit. The size of the orifice is adjusted by turning the adjustment screw that raises or lowers the needle, okay, as being shown here. If we turn in, okay, it is coming down and squeezing the passage, right? If we do it further, it can completely close it, right? Okay, so this way we can control the opening. If we unscrew it, the reversing will happen. Okay, and here is the graphical symbol, right? And this arrow, okay, says what? You know it, earlier we have used it in pump as well. It is variable type. That means the opening can be altered, okay, as we have just seen by unscrewing the knob, right? Okay, now one thing before I leave this slide: how do you know that how much flow is being shed there? When you turn the screw, when you screw in or screw out, yes, there are some type of charts available, or graduations are provided right at the top of the valve, as shown here. When you turn this knob, we can see, okay, definitely there will be this arrow, this graphic says that if we rotate it clockwise, flow will increase, and in a particular position how much flow it is allowing, it can be understood from this graduation, from this scale. Okay, here is the application of non-pressure compensated FCV. Non-pressure compensated FCV. Still, I have not discussed why it is called non-pressure compensated type. Okay, but its construction we have come to know. Application, very simple. Pump set, a DCV, and there is one actuator, linear actuator. But in the middle, there is one FCV. Okay, so definitely by controlling the opening of this FCV, we can control the speed of actuation of this actuator. Okay, Q by AP is equal to the velocity, right? Now think about the retraction stroke. The question raised, what about the retraction stroke? This FCV is fitted before the blanket side. Okay, what for? What is it for? Apparently to control this extension speed of the piston. But the question raised, what about the retraction stroke? Think about that position of the DCV, this position. I mean, this envelope is in action. So flow now will take place through this, and will come to the rod end side, right? And piston, say piston is here, right? As oil is coming the rod end side, piston will be moving towards left, while from this side will be flowing out, but it is bound to flow through this FCV again. And these FCVs are not direction sensitive. From any direction, flow can be controlled. May it be from this side to this side, or from this side to this side. That means, though FCV is fitted here in the blanket side, even in the retraction stroke, it will work. That means it can even control the retraction speed, though fitted in the blanket side. Understood? But that may not be the case we wanted. Say we want a hydraulic circuit where forward stroke means extension stroke will be controlled. I mean, forward stroke will be controlled means speed of forward stroke will be controlled, and backward stroke means return stroke, means retraction stroke will be normal. How can I do this? Can you answer? Yes, you are right. Leakage probably it can be done with the help of a check valve. How? Here is how. Look over here. Say this envelope is in action. So flow will take place through this here. Check valve is fitted in such a manner that it is in no flow direction. So flow is bound to take place through FCV. It will enter the blanket side, and definitely by adjusting the knob here, okay, we can control the A0 area of the orifice, and thus speed of actuation, extension speed we can control. Understood? Now look over here. What about the retraction stroke? Consider this envelope is in action, as here it is being shown. Flow will take place through this, will enter here, and it will push the piston towards left, while from the blanket side will come out. But now see here, check valve is free flow direction. So definitely the flow from blank inside now won't be restricted as it was being restricted in previous case without check valve. Thus, retraction stroke speed will be as it is in the case of a normal double acting cylinder circuit. Okay, so that is another kind of FCV where FCV supplied along with a check valve fitted parallel to it. That is FCV with integrated check valve. Okay, so everybody here in these two diagrams, here if flow takes place from this side left to right, okay, it is bound to be controlled or restricted because it is no flow direction. Okay, as flow enters here, this path will be completely closed, so flow is bound to take place this path. Okay, but as flow enters here restrictions is provided, but it is free B to A, it is free flow direction, so definitely there will be free flow from right to left. Okay, what will be the graphical symbol of this kind of valves? Very easy, you can easily draw it. Okay, it's this. Okay, please check whether it is rightly drawn or not. Okay, now that question, why it is called as non-pressure compensated type, right? Why it is called as non-pressure compensated type? Basically, answer to this question depends on another observation. What is that? Observation is there is a common problem associated with it, and that is it is load sensitive. Load sensitive? What is that? And what is the relation of that with its name, like non-pressure compensated type? Okay, fine. Let me discuss about this. Here is once again similar hydraulic circuit with FCV fitted here, and there is a load, okay, as being shown here. Here is a load. Okay, what you are expecting is flow will take place through this, it will be pushing the load, right? Say assume we want some velocity of this load, so definitely the FCV is restricting its area, reducing flow through it to the desired one, which is required to create some extension speed of this piston, some moving speed of this load. And since we put some restrictions over there, this pressure gauge will read what pressure? Yes, PRV setting pressure. Say that pressure is 70 bar. Understood? That pressure is 70 bar. And assume the pressure needed to displace the load shown here is 30 bar. Okay, what is the pressure difference across the orifice? 40 bar. Okay, so we can find out Q through it. Okay, from that equation where del P was one function, we can put del P there. Okay, A0 area of the orifice also there. Now you see, please remember, I am not controlling A0 now. I won't be controlling A0, right? But what I'll do is I'll change the load. It may happen in industry when a hydraulic cylinder is made for that. Okay, not that always it will be displacing same load. It may vary. Say it is changing like this. Okay, see everybody. So the load has been changed, increased rather. Now increased load demands increased pressure. Otherwise, okay, this piston cannot displace the load because P into A is the load carrying capacity. I hope you can remember P into A is the force, hydraulic force acting on the piston, and that should be sufficient to displace the load. So if load increases, so P must increase. Okay, so demanding more P. Okay, and that can be readily seen in the pressure gauge downstream to the FCV. So it has been changed to 40 bar here. 40 bar. That is what it is expecting. Definitely, if you change the load such that it demands more than 70, then it won't work. Okay, I'm not talking about that also. I hope you can understand that. So now in this condition, it demands 40 bar. Okay, arbitrarily considered, but it is justified. But one thing you must have noticed, the del P, the pressure difference between these pressure gauges, across the FCV, now it has been reduced. It was earlier 40 bar, now it has been reduced to 30 bar. Pressure difference reduced to 30 bar. Since pressure difference reduces, Q through FCV also reduces. Because we have not changed CD, same as FCV, we have not changed A0, I mentioned, but pressure difference across FCV drops. So Q through it will drop. As Q will drop, so you can rightly guess, okay, the speed of extension of piston now will come down. Okay, so what happens with the change of load, with the increase of load rather, the speed of extension reduces. So definitely we can say with the reduction of load, speed of extension will increase. That is why it is being said that this kind of FCVs are load sensitive. Change the load, speed of actuation will change. Understood? Okay. That means it cannot compensate itself such that with the change of load, velocity, speed of actuation remains constant. It cannot compensate itself such that with the change of the load, velocity or speed of actuation remains constant. It cannot compensate. That is why it is called non-pressure compensated type. Okay, what we want, whatever may be the load, speed of actuation should remain constant. But in this type of valves, that is not going to happen. Okay, change the load, speed of actuation will change. Okay, you may think that if we control the area, if we adjust it accordingly, then definitely speed of actuation may remain constant. Yes, that's it, that's true. But that is not what we expect. What we expect is the valve will adjust itself in such a manner that with the change of the load, speed of actuation will also remain constant. And that can be done in pressure compensated type. And in pressure compensated type, everybody here, since we are not changing A0, in pressure compensated type, the pressure difference across the FCV will remain constant such that flow through it remains constant, and in turn speed of actuation remains constant. Yes, even with the change of the load. You may ask, how is it possible? So if we change the load, we have just seen pressure downstream to the FCV is changing. Yes, that is true. So what you have to do to keep pressure difference constant? Pressure upstream to it can be increased to keep same pressure difference as previous. Again, you can ask, sir, pressure upstream to the FCV depends on pressure relief valve. We are not going to change the relief valve setting. Then how come that pressure difference across the FCV remains constant? Definitely, that is, all of these are logical questions, but that will be discussed in the following slide. So that is the equation I have described using this, but here it is being shown. You can, I hope you can remember this and you can understand the logic what I have just explained. Now here is the pressure compensated type FCV, where that things are going to take place what we expected in my previous slide. Okay, here this is the main FCV, that is the main spool. Okay, that's the main spool. That's adjustable knob. By screwing in, screwing out, we can control this area. Okay, A0. But as I said, once this area is chosen, we are not going to alter it by turning it manually. Okay, so this A0 will remain constant. Right? There are two pressure gauges here, downstream to this FCV, that is upstream to this FCV. Right? Here is another pressure gauge. Yes, this is actually showing the pressure of pressure relief valve. This is not. Okay, so this is done so intelligently. Okay, you will come to know. Allow me to discuss. So pressure difference in these two pressure gauges we are going to keep constant, so that flow through it remains constant irrespective of the load here. Yes, this is symbolizing the load. Here is a motor, not a linear actuator, a motor. It is rotating, say, at 500 RPM speed with this load. Right? What you are expecting is, as we put some more loads here, its rotational speed will remain almost constant. And I should mention, pressure difference across this FCV will also remain constant because we are not changing area. Okay, so pressure difference must remain constant, otherwise flow through it shouldn't remain constant, because if we change the load, this pressure will increase. Right? It must increase. Okay, because I said earlier, more load demands more pressure. I explained with linear actuator, in rotary actuator, the same story. Okay, and since pressure increases here, so definitely pressure here should also increase to keep pressure difference constant, to keep flow through this constant, to keep rotational speed constant here. How is it being accomplished? That is different story. That will be explained in my following slide. But that is being done here. Okay. Let me show the these pressures with some other loads. That is this condition. Say load has been increased here, and thus pressure you see here 1400 psi. Here it was 1000 psi. Okay, 400 psi increased, right? But you see the speed 492 RPM, almost constant. With this huge change of pressure, speed almost remains constant, because the pressure difference across this FCV, it was 100 psi. Now here it is 1400, 1496, 96 psi. Almost same pressure drop. Okay. What about if we drop the load? Here it is. See, load are removed. Even then, speed remains 508 rpm, almost constant. And since load has been removed, pressure here also falls to 600 psi. From 1000 to 600, 400 drops. But since the speed remains constant because we have not changed this area, pressure difference across it remains constant. You see here 600, here is 704 psi, means 104, almost constant. But in all cases you must have seen this pressure showing same 2000 psi. What is that pressure? That is pressure relief valve. So basically here we have used another pressure gauge, okay, to show on intermediate pressure. Okay, this is basically fitted just upstream to the FCV. We have not fitted the pressure gauge only. We have used something else, and that is another spool. Not only this main spool, another spool here, right? And this is driven by a spring here. There is a pilot line here. All these are helping us to keep pressure difference across the main spool constant. How? Here is how. Okay, the same diagram I am using. Okay, so here is the pressure compensated flow control valves to overcome the difficulty caused by non-pressure compensated valves. Okay, I mean it works on a kind of feedback mechanism from the outlet pressure. Okay, it keeps flow through the orifice nearly constant. Schematic diagram of the pressure compensated flow control valve are shown here. A pressure compensated flow control valve consists of a main spool and a compensator spool. Okay, this is the main spool, this one is the main spool, and this is the compensator spool. Okay, the adjustment knob controls the main spool's position, which controls the orifice size at the outlet. So here is the main spool. Okay, right? By this adjustment knob we can control the main spool position, but once controlled we are not going to alter it, right? I mean A0 will remains constant. Okay, fine. Now allow me what is happening there. Okay, see everybody here, this is compensator spool, as I said, means it is movable automatically. You don't have to control it. It is driven by a spring. Spring is compressed, always forcing it towards left. Always forcing it towards left. Okay. And as this compensator spool moves towards left, you see here this opening can increase. As compensator moves towards right, this opening can decrease. Means when it decreases, flow through it will decrease. As it moves towards left, this opening increases, flow through it will increase. But no matter how is the opening, upstream to this opening, pressure will always be relief valve pressure, because it is coming from the pump. As this opening being controlled, then definitely extra amount should pass through pressure relief valve, and thus pressure upstream to this opening must be pressure relief valve setting, that is say 2000 psi. Now here, what are the forces acting on this compensator spool? Number one force acting from left to right. What is that force? That is one hydraulic force. Because of what pressure? Because of pressure here in this annular passage. It is acting on this compensator spool through this pilot line. Yes, through this pilot line it is acting over there towards right. Okay. Pressure acting on the compensator spool here, they are nullifying each other. Okay. Here it is acting towards left, here acting towards right. They are cancelling each other. Here we won't be considering them. Now flow takes place through this, through this, through this, here going to the load. There is another pilot line here. Through this spring, it is acting on the compensator spool again. So there will be another hydraulic force, and that is acting from right to left. This is because of downstream pressure to the main spool. That is the main spool, that is the downstream side. So this hydraulic pressure, hydraulic force, because of this downstream pressure, because of pressure downstream to the main spool, and this pressure is because of pressure upstream to the main spool. Here is upstream to the main spool, right? Apart from this hydraulic force, in the same direction the spring force is acting. Understood? Therefore, in equilibrium of the compensator spool, right in this position, we can write this: Pu into A is equal to Pd into A plus Fs. Pu is pressure upstream, red colored arrow. Pd is pressure downstream. Upstream, downstream with respect to what? With respect to main spool. P downstream into A plus Fs. Right? Now if we arrange this by some simple mathematical manipulation, Fs will be Pu minus Pd into A. That means spring force equal to pressure difference across the main spool multiplied by A. Right? So if we change the load over the motor, what will happen? Definitely pressure here must change because load has been changed. Okay, so pressure here must change to displace more load. Say, try to recall this part only. Okay, pressure is 14,000 psi here. As this has been changed, that means this has been changed. This is fairly constant. So definitely the compensator spool will be moving now towards left. How long will it be moving? Till it reaches the equilibrium. And when equilibrium will reach? When Pu, pressure upstream to this main spool FCV, will reach that value for which it will be equalized with Fs. But how can you say pressure upstream to it will increase? Because we have just accepted that this compensator spool will move towards left. As it moves towards left, this opening, okay, will increase. As it increases, flow through it increases, and thus pressure here will increase. Pressure here will increase. That means pressure here will increase. Right? So compensator spool is moving towards left till the same difference is reached. Okay, as same difference is reached across this main spool, flow through this will remain also same. Okay. Thus, this valve can compensate itself sensing the load. That means actuation speed irrespective of the load will remain same even with FCV. Okay, that is pressure compensated FCV. The graphical symbol. This one is the graphical symbol of compensator FCV. Okay, this arrow says it is pressure compensated type. Here, this is 1 second pressure compensated type, but check valve as an integral part. Okay, that is the graphical symbol. Okay, thank you. Okay, I will discuss some problems regarding FCV in my next